So here we are looking at lines and curves in space. So this is the first time that we are being introduced to a vector-valued function. So at this point in our calculus careers, we are super duper familiar with scalar-valued functions, something like y equals f of x. But this is our first encounter with a vector-valued function. So get excited. So to begin, we want to look at a line in space. So the general equation of a line in space is defined as the set of all ordered triplets x, y, z passing through a point P naught defined by the components x naught, y naught, z naught and parallel to a vector v. So how do we define this vector-valued function of a line? Well, the function itself is defined as vector r of t. And this is going to be equal to a position vector r naught plus t times the parallel vector v. This position vector r naught is the vector defined from the origin to the point P naught. So this will be the vector with components x naught, y naught, z naught. And then we have plus the parameter t multiplied by our parallel vector a, b, c. So using a little vector arithmetic here, we can distribute this scalar multiple, our parameter t, through to each component, which would rewrite this vector as at, bt, ct. And then using vector addition, we can now combine the like terms, or these like components, to get the vector-valued equation of the line. So this is going to simplify to vector r of t. And this vector, notice, has three components, x, y, and z. So we can think about this as x of t, y of t, z of t, where x of t is defined as x naught plus at. Y of t is defined as y naught plus bt. And z of t is defined as z naught plus ct. And now since this is a line, it extends infinitely in both directions. So this is going to be where t is an element of the open interval from negative infinity to positive infinity. So this is what we call the vector equation of the line. So the vector equation of a line in space. So a couple of little notes here. And I mentioned this as we were going, but this t is our arbitrary parameter. And it is a scalar. It's a real valued scalar. So t is an element of the real numbers. So the arbitrary parameter t is similar to x in the function f of x. Here, t is our variable in the vector valued function r of t. And now the position vector r naught, again, is the vector from the origin to that point P naught. So we can think about this r naught as being equal to the vector from the origin to point P naught. So if we think of the components here, this is terminal minus initial. So this would be x naught minus 0, y naught minus 0, z naught minus 0, which leaves us with that position vector x naught, y naught, z naught. So the last thing, before we look at an illustration of this equation of a line in space, I want you to note that the vector equation of the line is not an exclusive format for an equation of a line in space. We also have what we call the parametric equations of the line. So the parametric equations of the line are the individual components of the vector equation. So again, looking above, notice that your vector equation of the line has three components, x of t, y of t, z of t. So the parametric equations of the line are these individual components. So we have three. We have x of t, which is defined as x naught plus at. We have y of t, which is defined as y naught plus bt. And we have the z of t component, which is defined as z naught plus ct. So these three equations are the parametric equations of the line. And again, this is such that t is any real number from negative infinity to infinity. Now, if we had a line segment, we would need to be more careful with our bounds, as we will see shortly. But first, let's go ahead now and look at an illustration of this line so we can better appreciate what's going on, and then we'll jump into some examples. All right, so here we go. Let's think about what this equation of a line looks like in space. So we know two things right off the bat. We know that the vector valued equation of the line must pass through the point P naught, and it must be parallel to vector V. So let's say here's our point P naught. Now, keeping in mind what the vector valued equation of the line looks like, we know we need to achieve vector r of t is equal to that position vector r naught plus the arbitrary parameter t multiplied by vector v. So all we have is this point P floating around in space right now. So let's go ahead and define the position vector. So we know the position vector starts at the origin and ends at point P naught. So here is our position vector r naught. So in addition, we know that this line must be parallel to vector v. So let's suppose we've got some vector v over here. Now, how are we going to achieve a line passing through this point P naught and parallel to vector v? Well, remember that the position of a vector is irrelevant. So we can take this vector v here and put it right up at point P. So these two vectors are parallel to each other. You could also use your parallelogram rule. Right? We can think of this as vector r naught plus vector v. So this vector along the diagonal of the parallelogram is the vector r naught plus vector v. So that's close to what we're looking for, but not quite there. We need that arbitrary parameter t. How are we going to do this? Well, let's keep in mind that t is a scalar. So since t is an element of the real numbers, in other words, a scalar, we can make a note to ourselves that t times vector v and vector v are scalar multiples of each other. They're parallel. They exist on the same line. Woohoo! So, let's think about what about if we had a positive t value, a positive scalar multiple? Well, that means that the line is going to extend infinitely in the positive direction. What about if we now let that scalar multiple, t, be negative? Well, this is going to extend infinitely in the negative direction. Hey, we have a line. So this is the line vector r of t is equal to that position vector r naught plus all possible scalar multiples of the parallel vector v.